speak, it all began in May 2026, when something unusual appeared off the coast of Peru. Sea surface levels rose more than 6% in above the long-term average. The cause was Nandapos, a storm surge, but a massive body of warm water that had traveled across the depths of the Pacific Ocean and converged here. This bulge stretched hundreds of miles across. By then, the predictions were already multiplying. The strongest El Niño ever recorded, a winter that would flood California, a suppressed Atlantic hurricane season, a global food crisis, and possibly the hottest year in recorded human history. But in July 2026, the scientific picture changed. This was no longer just a possibility emerging from climate models. The ocean and the atmosphere had already begun interacting, and the threat had become real. So, the mystery is no longer whether El Niño will happen. The real question is how a patch of warm water located far from most of the world and Nandapos, major cities, can affect our homes, storm forecast, reservoirs, farms, and grocery bills, and most importantly, why scientists believe this is only the beginning, and that its greatest global impact may not be felt until 2027. According to the July assessment, the event is strengthening with a 97% chance of persisting through early spring 2027. There Andapos. Also an 81% probability that it will reach the very strong range between October and December 2026. Ocean surface temperatures are already above average across much of the central and eastern equatorial Pacific. Most importantly, a downwelling Kelvin wave has deepened the boundary between the warm upper ocean and the colder water below. This creates a reservoir of heat capable of fueling El Niño Andapos, continued intensification. That unusual bulge off the coast of South America was the first visible clue. The satellite was Nandapos, simply detecting unusually high sea levels. Warm water expands. So, the rise in sea level revealed a vast reservoir of heat moving eastward beneath the Pacific surface long before its effects reach the atmosphere. El Niño is no longer just a potential threat. Scientists are now focused on what will happen once it reaches full strength. At first, that may sound contradictory. The Pacific Ocean is warming in 2026, yet 2027 could see an even greater increase in global temperatures. El Niño transfers heat from the ocean into the atmosphere. That process takes time, and its effects can continue even after tropical waters begin to cool. A clear example came during the 2015 to 2016 event. It peaked in late 2015 and early 2016, while 2016 went on to become the warmest year ever recorded at the time. The same delay occurred after the powerful 1997 to 1998 event. First, the ocean changed. Then came the surge in global temperatures. But what is happening today is not a repeat of those events on the same planet. Greenhouse gases have raised the underlying baseline beneath all natural climate variability. The warm phase of El Niño adds a temporary boost on top of that long-term trend. The latest 5-year assessment from the World Meteorological Organization estimates an 86% chance that at least 1 year between 2026 and 2030 will surpass 2024 as the warmest year on record. And now a powerful El Niño peaking in late 2026 makes the following calendar year an obvious candidate. Whether 2027 actually breaks the record won in Nandapos be known for many months. El Niño will already be reshaping risk across both North and South America, and not always in the direction that people might expect. And that brings us to what seems like the first piece of good news. El Niño typically strengthens upper-level winds over the tropical Atlantic. This can disrupt developing storms by displacing them and separating their circulation from their thunderstorm activity. As a result, The 2026 forecast calls for a below normal Atlantic season with 8 to 14 named storms, 3 to 6 hurricanes, and 1 to 3 major hurricanes. That sounds manageable. Speak. But those numbers describe activity across the entire basin, not the risk of landfall. A single storm striking the wrong stretch of coastline can define an otherwise quiet season. Meanwhile, the outlook for the eastern Pacific is almost the exact opposite. Forecasters expect an above-normal season with 15 to 22 named storms and 9 to 14 hurricanes. A single ocean cycle can act like a brake on one side of the Americas and an accelerator on the other. But hurricanes are only one consequence of the atmospheric reorganization triggered by a warming Pacific. Farther north, the same large-scale shift begins steering winter storms across the United States. During a typical El Niño winter, the subtropical jet stream strengthens and shifts farther south. As a result, storm systems are more likely to track across the southern United States, increasing the chances of wetter conditions from parts of California to the Gulf Coast and the southeast. Farther north, the pattern often reverses. The Pacific Northwest, the Northern Plains, and the Great Lakes region tend to become drier, while much of the northern tier experiences warmer than average conditions. This combination matters most in regions where winter snow serves as a natural water reservoir. Across the Pacific Northwest and the northern Rockies, a warmer, drier season can reduce mountain snowpack. The effects may not be obvious in January. They become apparent later when spring snowmelt arrives earlier than usual or delivers less water to rivers, reservoirs, farmland, and hydroelectric facilities. In the Great Lakes region, warmer air and reduced ice cover can alter the timing of lake effect snow. Individual storms can still be intense, but overall, the season may bring fewer prolonged periods of cold weather and persistent snow cover. Southern half of the country faces a different challenge. The stronger southern jet stream can carry repeated storm systems from California across the Gulf Coast and into the southeast. One storm is usually manageable, but several storms hitting the same region in succession can saturate the soil, trigger river flooding, delay flights, close roads, and significantly increase the risk of flash flooding. Agriculture also feels the effect of this divide. Excessive rainfall can keep heavy equipment out of the fields or damage winter crops across the south. Farther north and west, reduced snowfall and precipitation can leave farms with less water available at the start of the growing season. So, the forecast isn't simply calling for a warm, rainy winter. It's about changing where water accumulates across the country and where too much of it falls all at once. And no state illustrates that imbalance more clearly than California. For years, California has learned to fear empty skies. Reservoir levels fall, wells are drilled deeper, fields are left unplanted, and entire communities begin watching mountains snowpack, the way people monitor a bank account. So, when El Niño raises hopes for a wetter winter, the first reaction is understandable. Finally, some relief. But California doesn't just need rain. It needs rain that falls slowly enough to soak into the ground, high enough in the mountains to build snowpack, and evenly enough to refill reservoirs without overwhelming the systems downstream. A series of powerful storms can produce exactly the opposite outcome. In February 1998, one of the strongest El Niño events ever recorded brought widespread flooding, landslides, evacuations, and billions of dollars in damage across California. Homes were destroyed not simply because water arrived, but because too much of it fell in the wrong places over a very short period of time. That's what makes the coming winter so challenging. After years of drought, the landscape itself may be less capable of handling sudden extremes. Burn scars from wildfires, dried out soils, aging leaves, and expanding development have all increased the number of places where heavy rainfall can quickly turn into a disaster. The real question isn't whether California will receive plenty of precipitation. It's whether that water will arrive in a form the state can actually use before it becomes something people have to escape from. And California is more than just a place where weather disasters happen. It is one of the country's largest agricultural regions, which means the consequences won't stop at the state's borders. An important thing to understand is that the supermarket shelves in Ohio don't need a flood for El Niño to affect them. The problems can begin thousands of miles away. Weak monsoon rains over major rice-growing regions, drought across Australia's wheat fields, warmer ocean waters driving fish away from the coast of Peru, or torrential rains destroying crops during the few critical weeks when they're flowering. At first, nothing seems to change. The shelves are still full. The same bags, cans, and boxes are still sitting where they always have. But behind the scenes, the numbers begin to move. Smaller harvests leave exporters with less to sell. Buyers begin looking for supplies elsewhere. Governments may restrict exports to protect domestic prices. Food manufacturers pay more for grains, vegetable oils, sugar, or animal feed. And these higher costs ripple through transportation contracts, warehouses, factories, and distribution centers. By the time the effects reach the supermarket, the hurricane or drought that started the chain reaction may already be months in the past and almost forgotten. For households, however, the results are immediate. A bag of rice costs more. A familiar brand disappears from the shelf. The sale price never comes back. Meat, eggs, and farm-raised fish become more expensive because the feed used to produce them has already become more costly. The first warning signs are already emerging. This spring, international rice prices increased as traders responded to the risk of insufficient rainfall across several major producing regions. Global harvest forecasts have also been revised downward compared with the record harvest of the previous season. That doesn't mean empty supermarket shelves are coming. The more likely outcome is a quieter, more persistent form of pressure. Fewer low-cost alternatives, smaller discounts, and another increase in grocery bills that many families are already struggling to manage. But some foods are far more vulnerable than others because much of the world's supply depends on just a handful of producing regions. So which foods deserve the closest attention? Most of the world's rice is grown in monsoon-dependent regions. In May, export prices for several widely traded rice varieties in Thailand rose sharply as traders began factoring lower rainfall into their expectations. And that happened before El Niño had even reached its expected peak. Wheat faces a different kind of threat. Australia supplies grain to markets across Asia and beyond. A dry growing season there can reduce the amount of wheat available for export, forcing buyers to compete for supplies from North America, Europe, or the Black Sea region. The consequences extend far beyond a bag of flour. Wheat is used to produce bread, noodles, breakfast cereals, animal feed, and thousands of other food products. A poor harvest in a single exporting country can therefore put pressure on entire supermarket aisles at the same time. The cooking oil market may react more slowly, making the warning signs easier to overlook. Palm trees can continue producing fruit after a short dry spell, but prolonged heat and water shortages may reduce yield several months later. If production declines in Indonesia or Malaysia, the impact will extend far beyond bottles of cooking oil. Speak palm oil accounts for roughly 40% of all vegetable oil traded worldwide and is found in nearly half of all packaged foods sold in supermarkets. Then there is fish meal, a product, the tandapos, almost invisible to consumers, but deeply embedded in the global food system. Under normal conditions, cold, nutrient-rich waters rise along the coast of Peru, supporting enormous populations of anchoveta, the local anchovy species. During El Niño, warmer surface waters can weaken the upwelling, pushing the fish into deeper water farther offshore, or beyond traditional fishing grounds. Anchoveta is rarely sold directly as food. Instead, itandapos is processed into feed for farm salmon, shrimp, poultry, and pigs. Fish meal typically makes up no more than about 5% of poultry and pig feed by volume. However, because itandapos far more expensive than most other feed ingredients, it can account for about 10% of total feed cost. As a result, even a 50% increase in fish meal prices can significantly raise overall feed expenses. Aquaculture is a different story altogether. Fish meal often makes up a much larger share of feed for farm seafood, while feed itself can account for as much as 60% of production cost. That means a major decline in Peruandapos and Anchoveta catch could lead to a much sharper price increase for farm-raised fish and shrimp. Coffee, cocoa, and sugar add another layer of complexity. These crops depend on narrow temperature ranges and precisely timed rainfall during flowering and fruit development. Just a few weeks of unfavorable weather can reduce an entire Sesonandapos harvest, but none of these products has to disappear from store shelves for consumers to feel the pressure. The real danger lies in the accumulation of problems. Rice prices rise a little, then vegetable oil becomes more expensive. Higher feed costs push up the price of meat and eggs. Coffee or sugar adds another increase. Each change by itself may seem manageable, but families donandapos shop for one product at a time. They buy an entire basket of groceries, and when several key ingredients become more expensive at once, more complex products made from them, bread, frozen meals, snacks, confectionery, and processed meat products, can all absorb rising costs from multiple ingredients simultaneously. That, and APOs, the moment when prices stop creeping up and start jumping. But poor harvests are only the first stage. The bigger shock may begin when governments respond to rising prices by trying to protect their own populations. A major producer may restrict exports, impose new export taxes, or temporarily ban shipments of certain food products altogether. From a domestic political perspective, that decision may seem entirely reasonable. Keeping more rice, wheat, or vegetable oil inside the country can slow local inflation and reduce the risk of shortages. But every shipment that stays home is also a shipment another country was counting on receiving. Importers suddenly find themselves competing for what and APOs is left. Traders rush to buy supplies before prices climb even higher. Other governments begin building emergency stockpiles. Exporters that remain open to international markets discover that buyers are willing to pay more. The original harvest losses, Haven and Andapos, changed. What has changed is the number of people competing for the remaining supply. During the 2007 to 2008 global food price crisis, export restrictions affected roughly 16% of the calories traded on international markets. Rather than containing the disruption, those measures helped spread it from one national market to many others. Rice is especially vulnerable to this kind of reaction. Most of the world andapos rice is consumed in the same countries where itandapos is grown, leaving only a relatively small share available for international trade. When a major exporter removes part of its supply from the global market, buyers cannot simply replace millions of tons overnight. And the United States does not have to experience food shortages to feel the effects. Speak. Domestic producers sell into markets linked to international prices. Food manufacturers compete for imported vegetable oils, food additives, seafood, and animal feed. As global buyers bid prices higher, keeping those same ingredients within the country becomes more expensive as well. At that point, El Niño is no longer acting alone. Governments react to markets, markets react to forecasts, and buyers react to one another. Poor harvests can push prices higher. Fear can make them soar.